Hello ladies and gentlemen, welcome to day 2 of graphing parent functions. This is section 1-5 in your pre-calculus book. Again, when we are looking at parent functions, we're talking about the function on which all other similar functions are based. So one thing here, we are not going to be using these other things. We're always going to be making a basic table and then adjusting that table using the values of A, H, B, and K. So we're going to do 4 examples here. We're going to do each of them on their own slide, but just so we remember, we are going to go in here and we are going to recognize the values of A, B, H, and K. Remembering that the H value always changes signs unless it is written in function notation. So these are all just straight up equations, which means we can go in and recognize our A value, our B value, our H value, and our K value. Remember that A is the vertical stretch factor, B is the horizontal stretch factor, H is the horizontal shift, and K is the vertical shift. So, let's jump right in here. That first example says y equals the absolute value of x minus 1 plus 2, which means we're looking at the absolute value parent. Remember that the absolute value parent function consists of the points negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. Because when we feed the x values into the absolute value parent, which is the function f of x equals the absolute value of x, what happens to those x values is that the sign, the negative sign, gets removed, which means it doesn't affect 0 or it doesn't affect positive numbers. So when we're looking at this particular example here, we have no number listed in front, which means A is 1. We have no number listed in front of x, which means B is 1. We have H equals positive 1, because we always change the sign on the H. And K equals 2, because we never change the sign on the K. So when we carry out our transformation to get our new table, remember that what we're doing is we're taking x divided by B plus H and A times Y plus K to get our new X and Y values. Now in this case, because B is 1 and H is 1, X divided by 1 plus 1 would really just be X plus 1. And then A times Y plus K, A is 1, K is 2, means we're looking at Y plus 2. So our new X values, each X value from the previous table would have 1 added to it, which would result in the numbers negative 1 through positive 3, because negative 2 plus 1 is negative 1, negative 1 plus 1 is 0, etc. And for the y's, we're going to add 2 to each of those values. 2 plus 2 is 4, 1 plus 2 is 3, 0 plus 2 is 2, etc. That gives us these 5 points, negative 1, 4, which is here, left 1 up 4. 0, 3, which is just up 3 from the origin. Right 1 up 2, 1, 2. Right 2 up 3, and right 3 up 4. Draw your absolute value function passing through those points. Again, we should recognize that distinctive V shape to the graph based on the fact that it is absolute value. Okay, our next example is a quadratic parent. This is a quadratic parent function. Okay, we recognize that we have a x squared term, which makes this a quadratic parent. That parent function is f of x equals x squared, which means our starting table is negative 2, 4, because when we square negative 2, we get 4. Negative 1, 1, 0, 0, 1, 1, and 2, 4. So then we go to the function itself and we recognize our A, B, H, and K values. So there's no number listed in front, so A is 1. No number listed in front of x, so B is 1. H is the opposite of what is attached to the x, which would be negative 1. And there is no number listed afterwards, meaning that K is 0. So when we're looking for what does that look like, what does our new function look like? Well, Again, we're going to take x, divide by b, and add h. We're going to take y, multiply by a, and add k. And this will work for any function. So x divided by b plus h would be x minus 1. And ay plus k would be just y. So the only thing that's affected here is the x. We're going to subtract 1 from each of the x values, which would change negative 2 to positive 2 into negative 3 to positive 1. And the y values are going to stay exactly the same. Graph those points, and we've got ourselves our picture. Okay, there is our parabola passing through those points. Okay, next up is the square root parent, the square root function. Remember that the square root function, we are looking for values that have a perfect square root. So there's only 4 points on the graph for the parent function. 0, because the square root of 0 is 0. 1, 1, because the square root of 1 is 1. 4, 2, because the square root of 4 is 2. And 9, 3. That makes up our parent function. Again, we then go over here and we identify our a, b, h, and k values. So a is 1, b is 1, h is negative 1, k is negative 2. And we use those to transform our parent function using our common rules. X divided by b plus h would be x minus 1, because x divided by 1 is still x, minus 1. ay plus k would be 1 times y, which is still y, plus negative 2, or y minus 2. So that would be negative 1, 0, 3, and 8 in the x column, and negative 2, negative 1, 0, and 1 in the y column. Negative 1, negative 2, 0, negative 1, 3, 0, and 8, 1 give us our nice square root function equation. The final example from the first page was an example of a reciprocal function. Okay, a reciprocal function. Remember that the reciprocal parent is a little bit different. Because we need to track the locations of a vertical and a horizontal asymptote, as well as what are called the corners. So 1, 1, 0 undefined, that's your vertical asymptote, is x equals 0. Negative 1, negative 1 is the other corner, and then undefined 0 will give us our horizontal asymptote. Now remember that when we carry out our transformation, we only alter the numbers. The undefineds stay in exactly the same place. So otherwise, this process is exactly the same. Okay, it doesn't matter what the parent function is. We are going to take the x value, divide by b, multiply, and then add h. And then for the y, we're going to multiply by a and then add the k. So with reciprocals, the a value is on top of the fraction, so that's a 1. The b value is still in front of x, that's a 1. The h value is the opposite of what's attached to x, that's positive 3. And the k value is what is listed after, which would be negative 2. So we're looking at x plus 3 and y minus 2 when we apply our x divided by b plus h, ay plus k. So we apply that to our numbers, giving us 4, 3, 2, and then that last line remains undefined, because again, that's still our horizontal asymptote. Our vertical asymptote is still going to be that second line. And then we have, for subtracting 2 from the y's, negative 1, undefined, negative 3, and negative 2. So what this tells us is that x equals 3 is the vertical asymptote. Okay, that is the line x equals 3. And the horizontal asymptote is the line y equals negative 2. So we draw those first. And then we graph the two remaining points, which are located at 4, -1 and 2, -3. Our graph will come in along the horizontal asymptote, pass through the corner, and exit along the vertical asymptote. Then we'll return on the other side of the vertical asymptote at the top, pass through the corner, and leave along the horizontal asymptote. So there's our reciprocal function. So we've done one of each. Now we're going to do a bunch more. They're going to be a little bit quicker. Again, it's going to be very, 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 very quick. The idea here is the same no matter what we do. We recognize the parent function, and we get the parent function table, and then we grab A, B, H, and K, and alter the table using transformations to create a table for our new function. So here we go. All right, so first up is an absolute value. So the parent function is the absolute value, which is f of x equals the absolute value of x. Remember, those 5 points are -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. We have A is 2, we have B is 1, we have H is -1, we have K is -3. So our new function, remember that we are doing x divided by b plus h and ay plus k. That would be x minus 1 and 2y minus 3. So the x minus 1 part, that's relatively easy. We subtract 1 from each value of x, which would give us -3, -2, -1, 0, and 1. And then for the y's, we're going to multiply the y value by 2 and then subtract 3. So 2 times 2 is 4, minus 3 is 1. 1 times 2 is 2, minus 3 is -1. 0 times 2 is 0, minus 3 is -3. 1 times 2 is 2, minus 3 is -1. 2 times 2 is 4, minus 3 is 1. Then we're going to graph those points. So -3, 1, -2, -1, -1, -3, 0, -1, and 1, 1. There again is our distinctive V shape. Notice that it has been stretched vertically by a factor of 2, creating a steeper picture, okay, than our example earlier. Second one is a square root parent. Meaning f of x equals the square root of x. Again, that is 4 points, 0, 0, 1, 1, 4, 2, and 9, 3. Then we have our a value is 1, our b value is 1, our h value is -2, and our k value is -1. So our new x divided by b plus h, ay plus k every single time. So in this case, since b is 1 and h is -2, that would be x minus 2. Since a is 1 and k is -1, that would be y minus 1. So we'd have -2, -1, 2, and 7 in the x column, and -1, 0, 1, and 2 in the y column. Graph those points, -2, -1. -1, 0, 2, 1, and 7, 2. And there's that parabola shape we come to expect on its side from the square root function. Last example here is a reciprocal parent. Remember that has 4 points as well, but 2 of them are actually the vertical and horizontal asymptotes. So 0 undefined, that's your vertical asymptote. And then undefined 0, that's your horizontal asymptote. So again, we go in here, we recognize that our a value is 1, our b value is 1, our h value is 1, and our k value is -3. X divided by b plus h, ay plus k would be x plus 1 and y minus 3. So we add 1 to the x's, 2, 1, and 0. The undefined remains undefined. And we subtract 3 from the y's, remembering that the undefined stays undefined. There we can see that our vertical asymptote is the line x equals 1. And our horizontal asymptote is the line y equals negative 3. Okay, so once we have that, I'm going to try to get this a little bit more dotted than it is currently. There we go. It's a little better. Then we graph our corners, which are located at 2, negative 2, which is right here, and 0, negative 4, which is right there. Again, it's going to come in along the horizontal asymptote, pass through the corner, and exit along the vertical asymptote, then return at the top along the vertical asymptote, pass through the corner, and exit along the horizontal asymptote. 3 more. Again, if you haven't done so yet, you should probably pause the video and try these 3 on your own, and then return to the video to see how you did. So our 4th example here of a try on your own is a quadratic parent. Okay, in other words, f of x equals x squared, which means our parent function is negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. We identify a, h, and k. So a, b, h, and k. So a is 1, b is 1, h is positive 1, k is negative 3. So x divided by b plus h, ay plus k, every single time, would be x plus 1 and y minus 3. So that would be negative 1, 0, 1, 2, 3 for the x values, and 1, negative 2, negative 3, negative 2, 1 for the y's. So negative 1, 1, 0, negative 2, 1, negative 3, 2, negative 2, and 3, 1. And that will give us our distinctive parabola shape that we're looking for in our new function. Okay, the next example is a square root parent. Remember, that is the function f of x equals the square root of x, and that for that function we use 4 points from the parent function, x values that have a perfect square, 0, 1, 4, and 9, resulting in y values of 0, 1, 2, and 3. Now, we have an a value of negative 2, we have a b value of 1, we have an h value of 1, and we have a k value of 5. X divided by b plus h, ay plus k. So that would be x plus 1, and then negative 2 times y plus 5. So the x column, we're simply adding 1, which gives us 1, 2, 5, and 10. The y values we're going to multiply by negative 2 and then add 5. So 0 times negative 2 is still 0, plus 5 is 5. 1 times negative 2 is negative 2, plus 5 is 3. 2 times negative 2 is negative 4, plus 5 is 1. 3 times negative 2 is negative 6, plus 5 is negative 1. So our points are 1, 5, 2, 3, sorry. I did 5, 1, not 1, 5. Come on, Wills. Okay, let's get that fixed. 1, 5, sorry. 2, 3, 5, 1, and 10, negative 1. Again, we have that distinctive parabola shape. The negative a value has flipped it vertically, creating the lower half of the parabola instead of the upper half. And then we have a vertical stretch factor of 2, as well as a horizontal and vertical shift. Okay, one more example, and that example is a reciprocal parent. Just another one. Remember that that is the graph f of x equals 1 over x. That has the two asymptotes and the corners in the table. Okay, that's the parent table for our reciprocal function. Then we go in and we identify the a value is 1, the b value is 1 because there's no number attached to x, h is -2, and k is 0, which means when we alter the table, x divided by b plus h, ay plus k, the only thing that's changing is we are doing x minus 2. The y is staying the same because a is 1 and k is 0. So that would be -1, -2, -3, and undefined. And then 1, undefined, -1, and 0. So our horizontal or our vertical asymptote is x equals -2. Our horizontal asymptote is y equals 0. The other 2 points are the points -1, 1 and -3, -1. So the graph comes in along the horizontal and exits along the vertical, passing through the corner on its way through. There you have it, folks. That is it, I believe. Let me check the next slide here. Yep, that is it for section 2, or set 2 of the section 1, chapter 5 notes for pre-calculus. Thank you very much for your time and attention.